Hello again and welcome. We're going to be looking at this pocket meter today. This is made by Woods. This is sold by Lowe's. One of the members on the EEV blog forum had pointed this out. It says perfect for household electrical testing. 10 function auto ranging. Looks like it'll read up to 600 volts both AC and DC and 200 milliamps for both AC and DC. I'm not sure if this is right. It shows 40 milliohms. That could be 40 mega ohms, I'm not sure. Frequency to 10 megahertz. Duty cycle to 99%. Capacitance to 100 microfarad. It has a diode test and continuity. We're going to be running this meter today against these three. I'd like to run it against one of Dave's new meters, but unfortunately it's not available quite yet. It's a 4,000 count meter. Again, this meter costs about $30. It's Cat 3 300 volt rated, and it's UL listed. The Syntec meters are not rated for anything. Of course, they're not listed either. But again, this is a free meter essentially. The two Flukes are both rated for Cat 3 600 volts, and of course these have been certified. None of these meters are true RMS. Now the 4 meters, the only one with a backlight is the Fluke 107. If you need to measure current, of course this can only read into the milliamps. Of course our Syntec meter can read 10 amps, but this is an unfused input. So again, you better be aware of that if you're using a meter like this. It does have a milliamp input, and that's shared with the voltage input. One of the things I don't like about that is if you select the current input and you're using these two inputs, you've just blown your fuse. And I suspect this is going to have the same problem. You put this thing over one extra click, you're probably going to take out the fuse. Of course, the Fluke 101 doesn't measure current, so that's not ever going to be an issue with this meter. And if we look at the 107, of course, it does read current, and it'll read up to 10 amps, but it doesn't have a shared input jack. Of course, the Syntec has a small, cheap glass fuse in it for the low current. This Fluke 107 uses a large HRC style fuse, and again, the 101 has no fuse. And this looks like it has a small ceramic fuse in it, again being UL listed. I assume that the ratings of that fuse are appropriate, but we'll take a look. Of course, on this channel I'm basically interested in the robustness of the meters. I ran one of these Syntec meters very early on in my testing. Back then I was using a 50 microsecond pulse width, but that was like the 10 to 90% decay. And I was using a 50 ohm source impedance with it, and I damaged one of these meters at 2 kV. I really don't know how low the voltage would have to go before a meter like this would survive. I've also ran these with ESD testing with a grill starter, and again I damaged them. So these meters are not very robust at all, but again they are free. Of course, this Fluke 101, this was the winner of my $50 shootout for robustness. This particular meter has still never been apart, still got the original batteries in it. I exposed this meter to a 13,000 volt 2 ohm source impedance, 100 microsecond full width half height, and this meter survived. This Fluke 107, this was supplied by 5KY, and again this meter is very robust. This meter, I actually exceeded what I exposed the Fluke 101 to. I exposed this all the way to 14,000 volts with a 2 ohm source and 100 microsecond full width half height, and this meter survived. This meter was eventually damaged. It took 15,000 volts to eventually take it out. Now, of course, I've repaired this meter since then, and it's fully functional. It's got some damage to the circuit board, which I've cleaned up, but again, this meter would probably not withstand a pulse like that ever again. So let's go ahead and open this one up, and we'll have a look at it. Looks like it comes with a nice little case. Just looking at the leads that were supplied with it, you can see it has the nice little end cap on here. They do appear reasonably sharp. Boy, that wire's pretty thin. Not really suggesting that the quality of the wire is any better. These are a set of ProbeMaster probes. Of course, these ProbeMaster probes cost more than this meter does altogether. Looks like it also has a battery down inside of the case. I'm not sure if this has actually got one installed or not. Does not look like it. So this is the manual that comes with it. See, the very first half or 11 pages are written in English. Let's see, resistance, continuity, diode, duty cycle, and capacitance. 250 volts AC DC. I don't know if that means that the meter's supposed to survive in those modes with 250 volts applied to the input of the meter. Of course, I run that test, so we'll find out. Under safety, it says it complies with UL 61010-1V3 for measurement category 3, 300 volt, category 2, 600 volt, pollution degree 2. What I don't see is where they call out any of the EMC testing. So unfortunately, I don't know if the meter is actually going to survive our ESD testing or not, but I guess we'll find out. Normally I put the cover over just the display, but boy, this thing's covering the whole meter. Because on the back side we can see made in China, distributed by Southwire. Calls out the 200 milliamp 600 volt fuse. You can see they are using metal inserts for the battery cover. That just tucks right into that slot. That's pretty nice. If we look at the banana connectors, you can see there's nothing on the bottom of this. It's just basically cantilevered out there in the air. You can see it's got like a little clamshell. Clamps around this piece of the connector. And so I don't know if this will show up on the camera, but it is a 200 milliamp 600 volt fuse. You can see it has the safety logos on it here. It's kind of an interesting design how they're hooking into it. I'll tell you, it's very dense in this area. So you can see here's the input. It goes through this PTC, and then from the PTC right here we got our high voltage resistor, and then this connects down to this MOV, and then the MOV runs through this real tiny trace over to this point here. Of course, we have another MOV which tacks into it, so that's going off to some other circuit, and then this point runs over here to this MOV. So these two MOVs, it looks like, are shared to a common point to this MOV, which then goes back to the return point. But boy, that trace is not very big. You can see they've got their stack of resistors here. This is their high voltage chain. So it comes again from this input here, through the chain, through this trace here, which goes up to this side of this MOV, and then of course this is back to your common point for this MOV. My guess is this Q5 and Q4 make up one of the high-speed clamps. It's possible too that these two transistors here, they call them diodes, D6 and 7, it looks like are also another high-speed clamp. Well, that is one tiny little beeper. You can see it has several trimmers. There's one here, here, and up here. So I assume that you could actually go in and realign this meter if it needed it. It's kind of interesting too. I've never seen a fuse holder like this. I bet you that's unique for this design. One of the things I don't like is the clearance in this area. You can just see how tight all this is. I would imagine if I pulled the fuse out, this thing is still going to arc. Either up in this area here. Well, I don't know. I could see this even arcing between here and here. Again, it's just so small. They're pretty limited on what they can do with these. So I thought what I'd do is take these 3 meters apart and kind of give you an idea of what the differences are. First thing you notice right off the bat is this small glass fuse inside of the Centec meter. Look at the size of that compared to this big HRC fuse. Down here we have the small ceramic fuse. But then the other thing we notice is look at the density of this board. Notice all these cutouts with the plastic inserts. Lots of room. So if you want to know how this meter survived that 14,000 volt transient, just look at the clearances and the creepage for this circuit board. This thing is made to survive those transients, that's for sure. You compare that with like this Free Harbor Freight meter. First of all, there's no fuse even across this shunt. See how tight everything is? If I hit this thing with that 14,000 volts, it would just arc across all this area anyway. You can just see the density difference between the wood and this Fluke 107. Just all kinds of room in this, very tight. So again, this surviving a 14,000 volt transient. We don't know yet what this will survive, but I can pretty much guarantee it's not going to survive what this meter can survive. Well, let's see if she'll power up. It looks okay. There's your continuity. Non-latching type. So, of course, it's fairly fast. Because that current input is shared with this common input, you throw this thing, and if there's not enough clearances in here, yeah, I don't know. I'm assuming that we're probably going to damage this meter. I think what I'm going to do is probably run this on that half-cycle line simulator, even with the fuse in there, and let's just see what happens with this. Even if the meter fails at some point, it's not really going to matter for that test. So let's just check this thing for accuracy. Again, this is with a short. We don't really need to clear it out. It's reading 0, so let's try it with a half ohm resistor. That's pretty good. Right there, 0.5 ohms, 0.6. This is with a 1 ohm resistor. It's pretty good, 0.9 ohms. This is a 50 ohm. Looks pretty good, 49.9, 100 ohms. Moves around a little bit. 1K, 997, looks pretty good. 10K, dead on. And all these resistors in the box are 1% or better. That's 100K, so 99.9. So 1 meg. Looks pretty good. 103. And this is a 10 meg. 9.96 it looks like. 97. It's diode check mode, so again this will be a short. Looks fine. And this will be a single diode. Looks good. Let's try it with 2. Nope. So its open circuit voltage is pretty low, it looks like. Can't read 2 diodes in series. Let's just try the capacitance mode. So this will be a 150 picofarads. It's pretty impressive. So it's reading 180 picofarads. This will be a 1 nanofarad. Looks pretty good, 1.16. This will be a 0.1 microfarad. Again, looks pretty good. It's with a 1 microfarad. Again, looks good. This is a 10. Looks real good. And this is with 100. Takes it a while, but 98.3 looks good. It's pretty slow, but it got there. So currently I have all 5 of these meters attached in parallel, and they're connected to my Fluke standard. And you can see I'm outputting roughly 10 volts. You can see they're all reading roughly the same value. It looks like the Centak meter is about 100 millivolts low compared to the other 3. But not too bad, I guess, depending on what you're going to use the meter for. So this is with 1 volt applied, and you can see again all 4 meters are reading a little bit low. Not too bad though. This guy's definitely the low one. So this is with 1 millivolt DC applied, and you can see the Woods meter is definitely able to pick this up. Of course our 2 Flukes can't do this. They don't have a millivolt range. They do have millivolts for AC though. It looks like our freebie meter in this range is also doing pretty decent. Let's just try this with our little reference box. This has been modified. You can see it can actually output an AC signal now. So because these 4 meters are not true RMS, I'm expecting them to display roughly 2.75 or so volts. So let's just see. Yeah, it looks real good. So 2.749, so very accurate. Now we can see on the Bryman, it's reading 2.492, and that's because this is a true RMS meter. This is actually the correct value. So this box is actually putting out a 2.5 volt RMS signal, but it is a square wave. So the way that these averaging meters work, they essentially multiply the input value by pi over the square root of 8, or 1.111, and that's how they calculate the RMS. So if this were a sine wave, these would actually display the RMS value. So let's try it without the DC blocking capacitor. This should read the same value. Now we can see our freebie meter is reading actually 5 volts. And I'm not sure why, but it looks like they are not able to handle that DC bias. So of course this square wave is being driven off a high-speed CMOS, and that's running off a 5 volt supply. So yeah, this meter is not able to handle that DC bias. But you can see the other three, there's basically no effect. So let me just switch this down. You can see we're getting the same value. Now on the Bryman, we can see the DC value down here actually changes to roughly 2.5 volts. So this meter is able to handle that just fine. Of course, these free ones that people like can't do this, so just be aware of that if you're using one of these meters. What I'm going to do is switch this down to 30 hertz, and we're getting roughly the same value. And let's try this at 15 hertz. You can see how the two flukes are actually starting to roll off for the low frequency. See, it's a 2.73. As I go to 15 hertz, you can see it's 265, 268. Again, this little Woods meter, it's not having any effect. So let's try looking at frequency again. This is the AC coupled output of the box, and this should be 60 hertz, and we can see it's 59.98, 59.9. Of course, the Syntec meter doesn't have a frequency mode, but again, we can see the two flukes are able to read this at roughly 60 hertz. Let's try this with the DC bias. Again, no effect. This will be at 30 hertz. Again, no problem. It looks like the Fluke 101 actually falls out with this though. This will be at 15 hertz. Again, no problem with this Woods or the Fluke 107. So I think the problem with the Fluke 101 is it actually needs that waveform to pass through the zero cross. So we can see here it's reading roughly 60 hertz. Again, this is with the DC bias. And you can see it's basically reading nothing. It latches the value. Okay, so I've got all these meters attached to my RF generator right now. And you can see I'm outputting roughly 1 kilohertz. And let's just see how high a frequency this thing can actually handle. It's pretty impressive. So this is 10 megahertz right now with all these in parallel. We'd actually have to start being concerned about the cabling. So I think that that's part of our problem. Let's just take it on up a little higher. Oh, so there's 15 megahertz, and we can see it's starting to have an issue. Let me just connect this directly to the generator. Oh, there you go. 15 megahertz, no problem. This is with it attached to my other RF generator. You can see I'm above 20 megahertz now, and it's not really having a problem with it. It seems to conk out at about 30 megahertz. So pretty impressive. So currently all 5 meters are attached in parallel. I'm applying a sine wave of 60 hertz. There's no DC bias. You can see it has an RMS value of 1 volt. So what I'll do now is increase the frequency, and let's see what the 3 dB point is for this meter. Looks like right about here, so you can see it's roughly 6.7 kilohertz, and we're reading roughly 0.707, and that's on par with our two Flukes. The Fluke 101 looks like it's doing a little bit better. Of course, our Syntec meter isn't really accurate enough to make these measurements at this low of a voltage, but again, it's a free meter. Okay, so you can see I have my new ESD gun out. Now we're not going to be using this to do static discharges just yet. That'll come later. but you may recall that this actually has a DC supply that I have access to. So what I'm going to do is apply a DC input to all 5 meters, and let's just see if this can handle the 600 volts that they rate it for. And again, this display isn't real accurate, but 492 volts right now. Again, our freebie meter is reading a little low. Let's take it on up a little higher. Of course, they only rate this meter for 600 volts maximum, but I'll bet you it can handle more. See, our 2 flukes are now overranged. Centach meter is still holding in there, but this is roughly 800 volts right now. So this is roughly 900 volts being applied to the meter, and you can see it's reading it just fine. So I've been doing some RF sweeps with this little antenna, see if there was any areas that this thing was really sensitive to. And it looks really good, even in various modes of the meter. I don't really see anything that would really concern me. Some of the meters I've looked at, boy, they'll really go bonkers just holding the antenna near them. But this one looks pretty stable. Okay, I've got the meter attached to my transient generator. And what I'm going to do first is just apply a rectified 220 volt signal. And you can see it's reading roughly 236 volts DC and 117 volts AC. So what I'll do now is rotate the knob through the functions except the milliamp range, because I'm sure that that would damage it. And let's just see if the meter can survive this. So it is reading the 120 hertz correctly. Don't smell anything. Looks fine. I'll go ahead and turn that off. And let's just do a functional test on this real quick. Of course, we're pretty sure that the voltage input does not have a problem, so this will be the 5 volts DC, and we can see it's dead on. And this will be with AC. Looks fine. And this will be the DC coupled. Let's just try frequency. That looks good. Should be roughly 50% duty cycle. And here's a single diode. Let's try continuity. Well, you can hear how quiet that is. Let's just compare that with the Fluke 101. And this is the 107. Yeah, that little beeper doesn't do real well. Let's try capacitive mode, and this will be our 150 picofarads. That looks fine. 1 nanofarad. That looks fine. 0.1 microfarads. That looks fine. So our 1 microfarad. So with our 10 microfarads. This is with 50 ohms, 100 ohms, 1k ohm, 10k ohms, 100k ohms, 1 mega ohm, and 10 mega ohms. Yeah, so the meter looks like it passes functional just fine. So you're probably used to seeing this. This is my grill starter, and this is basically how I've been conducting the ESD tests on these meters. So this thing only puts out about an amp peak at maybe 5 nanoseconds wide pulse. So it really isn't representative of the test that these meters would normally go through. So I designed this generator which will output a 15 amp peak in under 1 nanosecond. And it closely matches the IEC standards for the decay. It's a little weak, but it's a lot closer than what this grill starter is. So what we're going to do is we're going to apply this directly to this meter. So what I'm going to do is apply 5 transients, both positive and negative, same way I always have. So we'll start it in resistance, and again this will be 5 transients. Then I'm going to reverse it. And that's it. Let's go ahead and functional test it. Again, this meter is not specified to pass the EMC standards. So this is with 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, and 10 megs. This will be diode check. This is with a short, and this will be a single diode, continuity mode. Looks fine. And let's try 150 picofarads. That looks good. Let's just do it with a 0.1. Yep, that appears fine. Just looking at the voltage mode, this will be 5 volts DC. That looks good. And let's try the AC mode. That looks fine. It's DC coupled. Let's try frequency. And that looks fine as well. So no damage to this meter off of the new gun. So this is the first real meter that we've tested. Pretty happy with that. Now, of course, this meter here would be damaged by this gun. I'm not even going to try it. I've got enough experience with those Harbor Freight meters to know what they can and can't survive. Let's just try it on our Fluke 101. And again, we'll flip the polarity. So let's have a look. This will be our AC volt. Again, 2.7, looks fine. Let's check the frequency. 60 hertz, yep, that's fine. And DC volts, that looks fine. I have a millivolt test on this. Let's just see if this works. About 130, yep, that looks good. And let's try it in resistance mode. Here's 50 ohms, 1K, here's 100K, here's with a 10 meg. Continuity's fine. Diode check with a short, and here's a single diode, a couple of diodes, no problem. Here's with 150 picofarads. Let's just try it with a 0.1. Looks fine. So, yep, so no damage to the Fluke 101. Again, I wouldn't expect there would be. This meter would have been through this same test, actually a little bit worse than what this generator puts out. So just so we're playing fair with all the meters, I'll go ahead and run the Fluke 107 as well. We'll change the polarity. And that's it. We'll go ahead and have a look, make sure it's still functional. So this will be roughly 2.75. And this is with the DC coupled output. Oh, let's just try the frequency. It should be 60 hertz. Looks fine. Here's 30, 15, 120. Let's try DC mode. Should be 5 volts. Looks good. Millivolts. This will be about 130. That looks good. And resistance mode. Here you have an open. Let's just try it with 50. And 1K. Here it is with 100K. And here's a 10 meg. Let's try the continuity test. So that's fine. Diode check modes. Here's a short. Here's with a single diode, 2 diodes, 3 diodes, no problem. This is a 0.1 microfarad. So yeah, it looks fine. Here you can see I've got the transient generator all powered up. And it's connected to our wood meter. Of course, we've got the high voltage probe. And again, that's attached to our oscilloscope. So we're going to start our testing with 1000 volts, 2 ohm source, 50 microsecond full width half height. Again, this will be 5 transients, both positive and negative, in all modes of the meter except for the current input. Wow, look at this. We already damaged it. You can see nothing plugged in. Yep, dead short. Continuity is a short. Let's try DC voltage. So that reads correctly. Let's try AC. That's correct. And let's try it in frequency. That is dead. And this is the DC coupled, and that does not work as well. So yeah, it looks like the hertz and all of the resistance, the diode check. I'm sure the capacitance has also failed. Probably everything in this mode. Let's just see, this will be a 1 nanofarad capacitor. Yep, can't read it. Alright, so looking at the meter, it appears that we've damaged a few of the transistors. We can see between this pair here, that's a dead short, and same with here. And this set over here are also shorted. I guess as we took out all four, this clamp that's located up here, you can see this one still seems to work correctly. So I think what we're going to do is go ahead and pull all four of these, and then we'll check them outside a circuit, and we'll look at replacing them. Those transistors are marked 1BW. That looks like a BC846B. That's a NPN 80 volt 100 milliamp part, 250 milliwatts. So fairly common part. I've got some here if we need them, so we'll go ahead and have a look. These end pieces don't want to come off of here, so yeah, I'm not going to take the time to pull them. Let's just have a look. And yep, that one's a short. And yep, that one's shorted. And that one is shorted. Yep. So all four of these are bad. They all have to be replaced, and then we can refunctional test the meter. So let the soldering iron warm up a little bit. And that should be that. So again, these are the four transistors I removed. And again, they're marked a 1BW, which I believe is a BC846B. And that is what I've replaced them with. So again, it's these two and these two here. We'll go ahead and reassemble the meter and see if it'll pass functional test. Okay, let's try the frequency setting. There we have it, 60 hertz. And this DC coupled, 30 hertz, 15, 120, 240, no problem. Let's try the voltage input. So again, this will be 5 volts DC. This looks good. And let's try the AC mode. 2.7, yep, looks fine. And this DC coupled again. That looks good. Alright, so let's try the resistance mode. Here's 50, 100, 1K, 10K, 100K, 1 meg, 10 meg. Diode check. Notice it's an open. Here's a short. And here's a single diode. Continuity test. And capacitance mode. So here's 150 picofarads. 1 nanofarad. 0.1 microfarads. 1 microfarad. It's 10 microfarads. And here's 100 microfarads. So it looks like the meter is functional again. What I'm going to do next is just transient test it while it's in the voltage mode. So you can see right now if I enable the output voltage, it's reading roughly 230 volts. So I've got the transient generator right now set for 1.5 kV. I'll just go ahead and run that. So again, this will be 5 positive transients only. And these are with a 50 microsecond full width half height and a 2 ohm source impedance. And you can see the meter is still functioning. The generator is now set for 2 kV peak with a 50 microsecond full width half height. And again, this is a 2 ohm source impedance. This will be 5 transients positive only. And again, you can see the meter is still functioning. You can just try the AC mode, and there's our 115 volts. So no problem. The generator is now set for 2,500 volts. And again, this will be a 50 microsecond full width half height, 2 ohm source impedance, 5 transients, positive only. And again, it looks like the meter is still functioning. Generator is set for 3,000 volts. Again, 50 microsecond full width half height, 2 ohm source impedance, 5 transients each, all positive. And again, it looks like the meter is still functional. And now I have the generator set for 4,000 volts peak, 50 microsecond full width half height, 2 ohm source impedance, again 5 transients, positive only. And again, it looks like the meter still functions. Alright, so the generator is now set for 5,000 volts peak, 50 microsecond full width half height, 2 ohm source impedance. Again, this will be 5 transients, positive only. Oh, there you heard it, something broke down. You can see the meter is still functioning. Let's try it in the other mode. So both AC and DC volts seem to work. This is with an open 1.3 k ohms, 1 diode. Looks like the continuity mode might still work. As you can see, this transistor is cracked. This one cracked. It's basically blown these totally open, and these two here are also damaged again. So all I've done is put the meter back together, and I've turned the generator on up to its maximum value, and let's just see if it'll break down repeatedly. You can see it looks like the meter still functions. So I've got the meter attached to our half cycle line simulator now. So hopefully here what's going to happen is the meter will break down one more time, and with that we're going to supply a transient off of this half cycle line simulator through it while the meter is in AC volts mode, and let's just see what happens. A little bit of smoke coming out of her. Looks like the LCD is still functioning though. Let's try this in the current mode. It's got the fuse in there. Let's just see what happens with that fuse. Looks like it dirtied up my leads a little bit. The switch feels pretty gritty. I suspect we're going to see quite a bit of damage around it. Ooh. See some of the debris down on top of the bench here. This all just came out of it. You'd think. Run one more transient with this thing open. We're going to give it one more transient off of this half cycle line simulator. Of course, there's no switch involved at this point. Everything is basically just opened up. Now that was loud. Couple of additional things about this meter. I measured the open circuit voltage while it was in diode mode, and it measured 1.456 volts. When it's in continuity mode, it measures 0.4485. It has a short circuit current of 229.6 microamps. In continuity mode, where the beeper is full on, it detects that at 7 ohms, and where it goes full open is 15 ohms. With a 50% duty cycle before it starts to alias is about 20 hertz, and it can detect a minimum pulse width of about 15 milliseconds. So you can see again some of the damage that's happened to this meter. Again, these transient generators are fairly low energy compared to what would actually be on the line. And even after the circuit board was removed from the case, so there was no switch or anything, you could see that the board would still arc over. Of course, the board had quite a bit of damage at that point. Of course, people have asked me in the past, well, why don't you run your fluke meters? Well, you know, I have. I've subjected this 101 and this 107 to the same transient, and these meters both had no trouble with this at all. Personally, I think if you were really looking for a good combination and you were working with just basic electrical stuff, I would get this 101, and I like this clamp meter that Unity puts out. This is the UT210E. Of course, this one is highly modified, so I've never actually measured voltage with this, but this is a pretty good meter. Use this in combination with this. You're going to have about $100, a little less than $100 invested, and you only use this for a clamp meter, and you only use this for your volts. It'd be a pretty good combination. So that'll conclude my testing for the Woods DMM W3 pocket meter. Hope you enjoyed the video. I'd like to welcome all you new followers. Till the next meter. Later.